You know, there's this question I can't stop thinking about, and it's not about whether aliens exist or whether we live in a simulation, though those are great questions. No, this one is more personal. What if you could go back just 10 minutes and undo that embarrassing thing you said, or forward 50 years to see if we figured it out? The climate, the wars, whether anyone finally invented a pizza that reheats well, time travel. We've been obsessed with it since H.G. Wells put a man in a brass machine and sent him screaming into the future. We've made 100 movies about it, written equations about it, argued about it over coffee. But here's the thing nobody tells you plainly. The physics of time travel is not science fiction. Some of it, a surprising, almost uncomfortable amount of it, is real physics verified, tested, sitting right there in our best equations about how the universe works. Now, does that mean you're going to step into a machine and visit dinosaurs? Well, let's find out. Before we talk about traveling through time, we should probably figure out what time actually is. And I'll warn you up front, this is one of those places where the honest answer is nobody completely knows. But here's what we do know, and it's already pretty wild. For most of human history, we treated time the way you treat the floor. It's just there. It passes at the same rate everywhere. 1 second for me, 1 second for you, 1 second on the moon, 1 second at the bottom of the ocean. Tick, tick, tick. Absolute, universal. Reliable. Isaac Newton believed this. He called it absolute time flowing uniformly, independent of anything external. And for everyday life, that model works beautifully. You don't need Einstein to catch a bus. But then 1905. A 26-year-old patent clerk in Switzerland, working in his spare time, writes a paper that quietly demolishes the idea of absolute time. His name, of course, is Albert Einstein, and the paper is Special Relativity. Here's what Einstein realized, and I want you to really feel this, not just nod at it. The speed of light is the same for everyone. Now that sounds boring, but it's catastrophically weird. Imagine you're standing still, and I throw a ball at you at 60 miles per hour. Now imagine you're running toward me. The ball hits you faster, maybe 80 miles per hour relative to you. Makes sense, right? Light doesn't do that. Whether you're standing still, flying in a jet, orbiting the Earth, or accelerating toward a star, light always travels at the same speed relative to you. Always 299,724.58 meters per second. And because of that one stubborn fact about light, Einstein showed that time itself must be flexible. Not metaphorically flexible, not time flies when you're having fun flexible. Physically, measurably. Mathematically flexible, the faster you move through space, the slower you move through time. This is called time dilation, and it is not a theory we're still debating. It's a measured fact. Your GPS, the thing that tells you to turn left in 300 meters, has to correct for time dilation every single day. The atomic clocks on GPS satellites tick slightly faster than clocks on the ground because they're farther from Earth's gravity and moving fast. If we didn't correct for this, your GPS would drift by about 11 kilometers per day. Time dilation isn't science fiction. It's in your pocket right now. So here's the first form of time travel, and it's real, it works, and nobody puts it in movies because it's too simple. Time travel to the future is possible. We've already done it. Here's how it works. The faster you move through space, the slower you age relative to someone who's standing still. This is special relativity, and the math is right there in the equations. If I put you on a rocket, and we're not being gentle here, I mean a serious rocket going, say, 99% the speed of light, and you take a round trip that lasts 1 year by your clock. When you get back to Earth, roughly 7 years have passed here. You just traveled 6 years into the future. Not by magic, by physics. Now you'd be thinking, okay, but I felt like only 1 year passed. And that's exactly right. That's the whole point. Time isn't absolute. Your clock ran slow relative to Earth's clocks. There's no correct version. Both experiences are equally real. The Soviets actually tracked this with cosmonaut Sergei Krikalev, who spent 83 days in space over his career. When he came back to Earth, he had technically aged about 0.02 seconds less than people on the ground. That's tiny, but it's real. The math checks out. Now at practical speeds, airplane speeds, rocket speeds, the effect is minuscule. You'd need to go absurdly fast to travel meaningfully forward in time. But there's a second mechanism that makes future time travel even more interesting. Gravity. Einstein's general relativity, published 10 years after special relativity, added something even stranger. Gravity slows time down. The stronger the gravitational field, the slower time passes. If you could hover just outside a black hole, close enough to feel the immense gravity, but not close enough to fall in, and stay there for what feels like a few hours, thousands of years might pass on Earth. This isn't made up. The movie Interstellar actually got this right. When they land on that ocean planet near the black hole, 1 hour there equals 7 years on Earth. Christopher Nolan's screenwriters read the physics papers. Kip Thorne, a Nobel Prize-winning physicist consulted on the film, so future time travel, real confirmed. Worked out mathematically, tested experimentally, the problem is it's one way. You can jump forward, but you can't come back. Which brings us to the hard part. Okay, this is where it gets complicated, and where I have to be careful to separate what the math allows from what physics actually permits, because going backward in time is a different beast entirely. Let's start with what the equations actually say. Einstein's field equations, the ones that describe how mass and energy curve space-time are, in a technical sense, symmetric in time. The math doesn't explicitly forbid backward time travel. In fact, there are solutions to those equations that seem to allow it. These are called closed time-like curves, or CTCs. A closed time-like curve is a path through space-time that loops back on itself. You travel forward through time and end up in your own past. Now this sounds like science fiction, but I want to stress. These come out of Einstein's own equations. A physicist named Kurt Gödel, yes, the same Gödel who broke mathematics, found a solution to Einstein's equations in 1949 that contained CTCs. Einstein was reportedly not thrilled about this. So how would you physically create a CTC? Theoretically, a few ideas exist. Idea 1, wormholes. A wormhole is essentially a tunnel through space-time, a shortcut connecting two different points in space and time. Einstein and physicist Nathan Rosen predicted these in 1935. They're called Einstein-Rosen bridges. You can think of space-time like a flat sheet of paper. Normally, to get from one point to another, you walk across the paper. A wormhole is like folding the paper so the 2 points touch and punching a hole through. Now here's the time travel part. If you hold one mouth of a wormhole stationary and accelerate the other mouth near the speed of light for a while, thanks to time dilation, the two mouths become offset in time. One end is in your future, one end is in your past. Walk through and you've gone backward in time. Beautiful idea, horrifying in practice. Here's the problem: exotic matter. To keep a wormhole open, to stop it from collapsing instantly, you'd need material with negative energy density, something that pushes space apart rather than pulling it together. We have hints that such stuff might exist. The Casimir effect shows quantum systems can produce tiny regions of negative energy, but an amount sufficient to hold open a traversable wormhole. We're talking astronomical quantities we have no idea how to produce. Idea 2, rotating black holes. A rapidly spinning black hole, called a Kerr black hole, has a ring-shaped singularity rather than a point singularity. Some solutions suggest that passing through the ring might allow you to emerge at a different point in space-time. Physicists take this seriously enough to study it, but the conditions inside a Kerr black hole would probably destroy anything attempting the journey. The tidal forces, the difference in gravity between your head and your feet, would stretch you into what physicists cheerfully call spaghettification. Not ideal. Idea 3, cosmic strings. These are hypothetical defects in space-time, infinitely thin, incredibly dense filaments that may have formed right after the Big Bang. Two cosmic strings passing near each other at high speeds could, according to some calculations, create a region where CTCs form. We've never detected a cosmic string. They might not exist, but we haven't ruled them out. But here's the thing that makes backward time travel really uncomfortable. The paradoxes, the most famous one you probably know, the grandfather paradox. If I travel back in time and through some terrible accident or unfortunate choice prevent my own grandparents from meeting, then I was never born. And if I was never born, I couldn't travel back in time to prevent the meeting, so they do meet. And I am born, and I travel back, and I prevent the meeting, and this paradox suggests backward time travel might be logically self-contradictory. Not just hard, impossible, because the universe would have to decide, do you exist or don't you? Now, physicists have proposed ways around this. Solution 1, the Novikov self-consistency principle. Physicist Igor Novikov proposed that only self-consistent histories are possible, meaning if you travel back in time, you can only do things that already happened. You can go back and watch history, you can interact with people, but you can't change anything because what you changed was already the result of your interference. Think about it. Maybe the reason your grandfather met your grandmother at that party was because you went back in time and introduced them. It's not a paradox. It was always the loop. This is actually internally consistent. The math works. But it raises a deeply strange philosophical question about free will. Solution 2, the many worlds interpretation. This comes from quantum mechanics. The idea is that when you go back and make a different choice, you don't change your timeline. You branch off into a parallel universe. The original timeline continues undisturbed. Your grandfather still meets your grandmother, but you're now in a new universe where they don't. No paradox, just infinite universes, which solves the paradox but creates other problems, mostly philosophical and financial, because you can never get home. Stephen Hawking's chronology protection conjecture, and then there's Stephen Hawking's take. He proposed that the universe itself might have a built-in mechanism, something he called the chronology protection conjecture, that prevents CTCs from forming. His intuition was that whenever you try to create a CTC, whenever the conditions are almost right for backward time travel, quantum effects step in and generate an enormous amount of energy that destroys the time machine before it works. The universe doesn't want time travelers, or rather it doesn't allow them, not because of a law written anywhere, but because the math naturally prevents it. He called it evidence for the existence of a cosmic censor. Hawking was being playful, but he wasn't joking about the physics. Okay, so where does all of this leave us? Let me try to be precise, because I think there's a temptation in both directions to be either too dismissive or too credulous. What we know for certain, time dilation is real, verified countless times. The faster you move, or the stronger the gravity around you, the slower your time passes relative to someone else's. Future time travel in a limited one-way sense is physically possible. We've measured it. What the equations allow but we can't do. Backward time travel is not explicitly forbidden by general relativity. Solutions to Einstein's equations that allow it exist, wormholes, CTCs. The math is there. What the physics probably prevents, the practical obstacles to backward time travel are so severe that most physicists believe it's impossible, either because of exotic matter requirements, paradoxes, or Hawking's chronology protection. We don't have a proof, but we have very strong suspicions. Here's my favorite way to think about it, and I think Feynman would have liked this framing. The fact that we can write down equations that allow backward time travel is incredible. It means time isn't what we thought it was. Space isn't what we thought it was. The universe has revealed that its geometry is far stranger and more flexible than Newton ever imagined. And even if backward time travel is impossible, even if the universe has some deep mechanism that prevents it, why it's prevented might teach us something fundamental about the nature of causality, entropy, and why time only flows in one direction. Why does time flow forward? We don't actually know. The second law of thermodynamics, entropy, always increases, gives us an arrow of time, but that's a statistical tendency, not a fundamental law. The underlying physics equations work equally well forward and backward, so why do we remember the past but not the future? Why can we influence tomorrow but not yesterday? These are not settled questions. They are active research areas, and they are connected to the question of whether backward time travel is possible. Time travel, it turns out, is not a silly topic. It's a thread you pull on, and the whole universe starts unraveling. So, can time travel actually be possible? The honest answer, the Feynman answer, is it depends on what kind forward time travel. Yes. Already real. Already measured. The only barrier is engineering. Backward time travel, the equations flirt with it, the paradoxes resist it. The universe might actively prevent it, but we don't have the final word yet, and that's not a failure of science. That's what science looks like at its frontier. It's not a wall, it's a door, slightly ajar, with weird light coming through it. What I hope you take away from this isn't a definitive answer. It's something better, a sense of how extraordinary the universe is, that the concept of time travel isn't nonsense. It's embedded in real physics, and chasing it has led us to relativity, to black holes, to the nature of entropy, to questions about causality itself. The next time someone rolls their eyes at time travel, you can tell them, Einstein's equations don't. If this made you look at your watch a little differently, that's the point. Hit subscribe if you want more of this real physics, honestly explained, without dumbing it down and without burying you in jargon. Drop a comment below if you could time travel forward or backward, where would you go? And why? I genuinely want to know. I read these, and I'll see you in the next one. Assuming, of course, that causality holds.